Hello and welcome. In this video, we are discussing designing FIR filter steps with example by windowing technique. Let's start. These are the steps we discussed in the last video. Always in FIR filter designing, we are starting with the given frequency response HD e raised to j omega. Its mathematical expression is equal to HD e raised to j omega is m e raised to minus j m minus 1 by 2 omega, where m is order of the filter, or we can say number of samples in HDN for given frequency range. Here it is for the low pass filter omega less than omega c, otherwise it is 0. Then the next step is to obtain HDN, we will apply the inverse Fourier transform to HD e raised to j omega. This is the inverse Fourier transform. Obtain the HDN is infinite in duration and non-causal. It is sync pulse. So it is infinite in duration and non-causal. To make it causal, we will add the shift, and the shift is m minus 1 by 2. So we will add the shift towards, we'll shift the sequence towards the right, and then we'll multiply with some window function. Here it is rectangular window is given. Due to that, we'll truncate the HDN to with the m samples. We'll plot the h of z, and from that we'll obtain h of omega. These are the steps to design the FIR filter. Let's start the example. Design a digital low pass filter for the following frequency response. So desired frequency response is given. HD e raised to j omega mod is equal to 1 for omega 0 to 0.4 pi, and it is 0 otherwise. Use rectangular window and assume m is equal to 5. M represent order of the filter. The first step, we will begin with the desired given frequency response. The mathematical expressions given are the mod HD e raised to j omega is 1 for 0 to 0.4 pi. Let's represent graphically. For 0 to 0.4 pi, it is 1, otherwise it is 0. Real-time frequencies are always positive frequency, but for mathematical expressions, we are considering the negative frequencies. For this given HD e raised to j omega, designing the filter means we are obtaining h of omega for this given desired frequency response, and this obtained h of omega, its frequency domain should satisfy these characteristics. To get the h of n, we will obtain inverse Fourier transform to this HDN. So the next step is determine the corresponding unit sample response HDN by applying inverse Fourier transform on HD omega. This is the definition of inverse Fourier transform: 1 upon 2 pi minus pi to pi HD e raised to j omega e raised to j omega d omega. We will put the value of mod HD e raised to j omega, and the range here, we know that our filter exists from minus 0.4 pi to 0.4 pi. The amplitude is 1 e raised to j omega. We will solve this integration. E raised to j omega upon jn, limits of the integration. Now we will put the limits of integration and we will get this equation. Now we know that e raised to j theta minus e raised to minus j theta divided by 2j is equal to sine theta. So we can express this in terms of sine. This HDN we are getting by evaluating the integration. This HDN we can obtain by generalized equation also, and the equation is sine of highest omega c of passband minus sine of lowest omega c of passband divided by pi n for n is not equal to tau, where tau is m minus 1 by 2. This is the given desired frequency response. So our equation will become sine of highest frequency is 0.4 pi n minus sine lowest frequency is 0 n divided by pi n. This term becomes 0. So our equation is sine 0.4 pi n by pi n for n is not equal to tau is m minus 1. M is 5 minus 1 divided by 2. That's why it is 2. And The highest frequency passband is 0.4 pi minus lowest is 0 divided by pi for n is equal to tau. So it becomes 0.4. So this is our sync pulse, which is infinite in duration and it is non-causal. Your HDN sync pulse, infinite in duration and non-causal. To this non-causal signal, we are adding the shift to make it causal, and this shift is m minus 1 by 2. And after getting the shift, it becomes causal. And now to make it finite, that means to select some finite samples of this HDN, we will multiply this HDN with some window function. Here it is a rectangular window function. So samples of HDN which lies within this window function will get selected, other becomes 0. So your first step is add the shift, and shift is m minus 1 by 2 shift to the HDN. That means we are replacing n in HDN by n minus m minus 1 by 2. M is equal to 5 here. So this m minus 1 by 2 becomes 2. So this is HDN and we added the shift. We replaced the n by n minus 2. This is the shifted HDN, that means causal HDN. And to this causal HDN, we will multiply by window function to truncate it with some finite samples. Before that, we will calculate m samples of HDN. HDN for n is equal to 0, 1, 2, 3, 4. M is 5, that's why 0 to 4. For n is equal to 0, we will put n is equal to 0 here and calculate the value of HD 0. Then HD n is equal to 1. Similarly, n is equal to 2, or we can say n is equal to tau. Now n is equal to tau or n is equal to 2, we will get 2 minus 2, 0. Sign of 0 upon 0. To solve this, we have to use L'Hospital rule. L'Hospital rule, denominator differentiation and numerator differentiation. So we'll get the differentiation of numerator, differentiation of denominator with respect to n. And now we can put n is equal to 2 in this equation. And we'll get the HD2. Similarly, n is equal to 3, n is equal to 4. So this is your HDN. HDN. Now the next step is define the window function. In the example, it is mentioned use the rectangular window for m is equal to 5. As we added the shift first, we will define the window function from 0. Otherwise, we have to keep the n is equal to 0 in the window function at the center, at the symmetric point. We added the shift first, so we can start the window function from n is equal to 0 to the m samples. And the next step is HDN we will multiply or truncate by window function by multiplying the HDN with the window function. This HDN, we have just calculated the 5 samples of HDN, but actually this HDN is infinite in duration. And we have considered just the samples from 0 to 4 as our m is 5. And we will multiply the HDN with the window function for truncation and we will get the h of n. We have just multiplied HDN with omega n or window function to get the h of n, which has only 5 samples. Here HDN is infinite in duration, but for convenience we have considered only 5 samples which we are considering. So this is your h of n, finite impulse response of discrete time LTI system. Next step is this h of n is finite and symmetric. You can observe this is the symmetry point. This h of 1 and h of 3 is same, h of 0 and h of 4 is same, and here the center of the symmetry. If we remember, in the previous video we have discussed that FIR filter has linear phase characteristics if it follows the condition h of n is equal to plus and minus h of m minus n minus 1. So this condition is satisfied here, means this designed filter has linear phase characteristics. The last step is find the h of z by using the definition of z transform. N varies from 0 to m minus 1 h of n z raised to minus n. And from that h of z, we can find, okay, first let's calculate the h of z. Put the value of h of n, h of 0, h of 1, h of 2, 3 and h of 4. And put the values, we will get this h of z. And in this h of z, to obtain the h of omega, we will replace z by e raised to j omega. And we will get the h of omega. Once you get the h of omega, you can compare the magnitude response of h of omega with the given desired frequency response, and if it matches, we'll stop here. If it doesn't matches, we have to assume some another order of the filter, and then we'll again design the FIR filter for another h of n. Like this, there is a lot of uncertainty in FIR filter designing, as there is no specified formula for order of the filter. In this example, we have designed the low pass filter with the rectangular window. Like this, we can design other filters also with some another window functions. In this example also, instead of rectangular window, you can apply the other window function also and calculate the h of n. Thank you.